Hi, everyone. It's an honor to be here to present our recent work, LAVA, Fine-Grained Indoor Wireless Coverage for Small IoT Devices. My name is Ivan, a PhD student at Yale University, and this work is a joint collaboration with my colleague, William Sussman, and my advisor, Wonjit Hu, at Yale University, and Jeremy Gumison at the University of Massachusetts Amherst, and Kyle Jamieson at Princeton University. According to a recent study, it is estimated that around 75 billion wireless IoT devices will be deployed by 2025. New consumer gadgets are deployed in an unplanned manner and crowd the unlicensed frequency bands. Endpoints used to be primarily near the human user, for example, laptops, phones, and smartwatches, roughly in the same 2D plane as the user. But now the endpoints can be about anywhere. For example, smart bulbs, smart plugs, and cameras. Endpoints can be near the ceiling, near the floor, and anywhere in between. Therefore, they can no longer be considered to be in the same 2D plane, but rather in a 3D signal space. This leads to non-uniform wireless 3D coverage. To illustrate this non-uniformity, we place an ESP32 Wi-Fi module at 30 different horizontal locations at desk level in a typical office space. We note in this figure that link quality varies significantly across locations. Moreover, if we repeat this experiment but place the Wi-Fi module near the ceiling, we note that the quality also varies significantly. And also if we put them on the floor. In a nutshell, at different vertical offsets from where a typical user is, antenna beam misalignment and obstacles exacerbate the non-uniformity of the signal coverage. What's more, some devices use, for example, Wi-Fi, while others use Z-Wave, Zigbee, and Bluetooth. That is, devices with diverse performance capabilities and standards share the same environment. Even devices that use the same wireless standard, in this case Wi-Fi, have wildly different performances. In this figure, we show the performance of 3 different Wi-Fi modules, and they're roughly co-located at 10 different locations, and we can see that they display completely different performances. These devices and other devices might benefit from improved coverage. The fundamental problem, to recap, is uncontrolled signal propagation indoors, resulting in complex, non-uniform 3D coverage. To provision high-quality coverage indoors, we need to address 2 challenges. First, we need to address the challenge of protocol agnosticism. That is, we need to improve communication between 2 endpoints, regardless of the specific wireless protocol provisions that they implement. This means that the improvement needs to occur below any notion of a physical layer unit. The second challenge is decoupling from the transmitter-receiver endpoints. In other words, signal improvements, the signal level operations need to occur independently from the endpoints themselves. The signal improvement that we might give needs to occur without modification to the endpoint operations themselves. This points towards modifications along the propagation path between the endpoints. Decoupling also implies no endpoint coordination. That is, we want to avoid getting any kind of channel information from the endpoints. So our solution is LAVA, a large array of vanilla amplifiers. LAVA is a mesh of multi-hop amplify and forward elements that are placed along the propagation path between endpoints. And it is able to handle the aforementioned challenges in the following ways. First, to tackle the protocol agnosticism challenge, LAVA remains protocol agnostic by relying exclusively on signal level operations. It simply boosts passing signals via successive amplify and forward. Second, to tackle the challenge of decoupling from the endpoints, it is a completely separate infrastructure from the endpoints. That is, the mesh is not connected to the endpoints in any way. but it is able to handle the signals along the propagation path between the endpoints. To avoid coordination with the endpoints, Lava also adopts power sensing to infer active transmissions without information from the endpoints. This allows it to work with off-the-shelf devices. Now let's take a look at the Lava design. As I mentioned, Lava is a mesh of devices, which we call elements. Let us start with the minimalist amplify and forward design, which we call a simple element. It consists of a fixed gain amplifier between a directional input antenna and a directional output antenna, and this is the basis of Lava's amplify and forward mechanism. However, this design is unidirectional since the amplifiers can only amplify signals in one direction. But we would like to amplify signals from and towards multiple directions. To do so, we use 2 stages of RF switches to integrate multiple directions into a single element. So instead of just having one directional input antenna, we have multiple directional input antennas, and the first RF switch selects which input antenna to use. The second RF switch allows us to select one of multiple fixed gain amplifiers, each of which is in turn connected to a different output antenna. Finally, by positioning the directional antennas towards different cardinal points, we can choose which direction to receive a signal from and which direction to send it to. So for example, we can decide to receive a signal on the north antenna and send it out the east output antenna. This design is what we call the multi-directional element. Now, each element, because its amplifier gain is fixed, has limited coverage. So we need a mesh of elements. The elements need to be organized into a suitable topology to extend the coverage area. When constructing the Lava mesh, there are 2 main considerations. The first one is the layout of the topology of the mesh. The topology layout depends on the element design. So we can have, for example, a complex that is multi-directional element design and a simple grid topology, as shown in this schematic and as built in this example testbed that we deployed on a ceiling. Or we can have a simple element design and a complex hexagonal topology, like the one shown in this floor deployment. The second main consideration when constructing the Lava mesh is the space that we leave between the elements. That is the inter-element or inter-hop spacing. The optimal inter-element spacing is where the signal amplification at each hop compensates for the path loss from the previous hop. Note also that a fixed gain amplifier also fixes the Lava mesh topology and the inter-element spacing. So that simplifies the construction of the Lava mesh. With a mesh topology, we then employ multi-hop amplifying forward to provide coverage around the Lava mesh and signal flow in any direction. Due to practical constraints, we deploy a planar testbed extended over a large area to provide horizontal coverage. Note that a dense topology will maintain good coverage between the hops. Finally, vertical coverage is provided by the vertical beam width of the directional antennas that we employ. Next, we explore how to control this mesh of amplifying forward elements. There are 3 main steps in actuating the Lava mesh. First, endpoint independent link detection. First, we detect the presence of an active transmission via per element power sensing and a centralized inference of active links. Second step is route computation. A multi-hop amplifying forward route between the elements closest to the endpoints is enabled. Route computation boils down to identifying the shortest route between the two elements closest to the endpoints. This is allowed by the grid topology, and it is indicated by the power readings of the elements closest to the endpoints. These power readings will be explained in just a bit. Finally, we just need to select the state of each of the Lava elements. Because the elements are built with fixed gain amplifiers, Lava adopts simple on-off switching of these amplifiers and the selection of the input-output antenna of the elements. Now let's take a look at some of the details. First, let's take a look at the Lava control architecture. Lava follows a hierarchical control network architecture. At the top lies a single master controller, which dictates the state of the entire mesh. That is, whether elements are on or off and which antennas are active. The lowest tier consists of microcontrollers, which act directly on the element's hardware and communicate with the master controller. Each element has a dedicated microcontroller, which uses an Ethernet connection to communicate with the master controller. For scalability, Lava can include an intermediate tier consisting of subcontrollers, each connected to disjoint subsets of microcontrollers based on physical proximity. Next, we will look at how each element detects active transmissions. Each element is equipped with a power meter that listens for active sessions between the inputs. Part of the input signal, in this case, shown in this figure, is fed into the power meter. The element's microcontroller samples the raw output voltage generated by this input signal at 16 microsecond intervals, generating the raw voltage profile shown in this figure. Then these raw samples are passed through fast and slow moving average filters. The element uses this filtered voltage profiles and edge detection to infer the presence of active traffic. If active traffic is detected, the element reports the difference between the minimum, the minimum voltage in this profile and the maximum voltage of as a metric of the signal strength detected by the element. With this mechanism, each element collects power measurements that are indicative of active transmissions and sends them to a central controller. So when the first endpoint transmits, the elements that detect the signal report power measurements to the controller. The controller then ranks these measurements and identifies the element closest to the first endpoint. When the rows of the endpoints are reversed and the second endpoint transmits a signal, the process repeats and the element closest to the other endpoint is identified. Note that the Lava topology serves dual purposes as well. It ensures coverage for both link sensing and signal amplification. After identifying the two elements closest to the endpoints, route computation is straightforward. Lava simply determines the shortest route between them. The controller then maps this route to active input and output antennas and amplifiers on the pertinent elements in the route, and a multi-hop amplifying forward path between the endpoints is enabled. Now, let us take a look at how Lava performs in practice. We run experiments using a broad range of devices to cover the spectrum of device capabilities and wireless standards. We run experiments in an office space area that encompasses 3 rooms and a corridor. And for the following results, one endpoint is placed on the ceiling and the other at various locations and different vertical offsets from the ceiling. The devices are placed at 40 locations, and the colors indicate the different transmitter and receiver pairings. This applies both to Zigbee and Wi-Fi. These endpoint locations shown in this figure correspond only to the subsequent result figures. Since LAVA is protocol agnostic, it provides substantial gains for Wi-Fi and Zigbee. LAVA increases the Wi-Fi SNR and the median is about 11 dB. LAVA also increases the Zigbee RSSI with a median of about 6 dB. This shows the protocol independent improved coverage across different vertical offsets and for different wireless standards. Now, let's take a look at how LAVA improves the performance of concurrent links on the same frequency. In this figure, each column indicates one of two concurrent links. As expected during concurrent transmissions on the same frequency, throughput is low. Now, for this setup, by enabling a LAVA route for each link, LAVA more than doubles the throughput when the links operate concurrently. When the links do not operate at the same time, that is not concurrently, and LAVA is inactive, throughput is higher than in the previous scenarios. But even in this case, after LAVA is activated, we can see throughput improvement on both, significant throughput improvement on both links, indicating that there's significant coverage improvement for those links. Across 5 different concurrent link setups, LAVA improves the per link throughput during concurrent transmissions by an average of 80%. There are many more results in the paper, so please refer to the paper for more detailed results. We discussed several other design issues, including 3D multi-hopping dynamics and link detection, false positives and negatives, among many other things. We also present many more performance results, including throughput enhancement, mobility, power offloading, and concurrent links in different scenarios and for different devices. So to conclude this presentation, we discussed how unplanned deployments lead to a lack of uniform coverage in 3D environments. LAVA addresses these issues via multi-hop amplifying forward and power sensing to provide fine-grained protocol-agnostic 3D coverage that is decoupled from the endpoints. Finally, LAVA delivers performance gains for diverse standards, different devices, and under different circumstances and scenarios. Thank you very much.